Good morning, good afternoon, good evening. I see we've got some attendees here from across the globe, so that's just wonderful. It's great to have you join me today. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging, and my topic today is those small field challenges and what you can do about them. Let me double check. Actually, my screen, yep, it's following my screens. Good. So let me stop before I get into that, the real meat of the topic here, just to say thank you to all of you for the work that you do. Cancer doesn't stop, even though a lot of the rest of the world is shut down. Our work, your work, is still very much needed, and we are here to support you. From our family here at Standard Imaging to your family wherever you happen to be. And a little bit of housekeeping as well. I am recording the webinar. If you have any questions, please feel free to enter them in the GoToMeeting dialog box. I will try and answer those as they come up if I notice them, but if I miss one, I will circle around back to that at the end of the presentation. If you aren't familiar with us, Standard Imaging is based in Middleton, Wisconsin. We have a pretty beautiful little campus here, although it looks a little more like that out the window right now. It's a nice, snowy, getting sunnier February day. Standard Imaging was founded in 1989 with just a few products, but has grown significantly since then, so that now we design and manufacture a full suite of QA products for radiation therapy. So, to the topic at hand, what makes small fields so challenging? Well, number one is size. It seems obvious, but it's true. Other issues that come up: source occlusion, energy changes, penumbra, loss of lateral charge particle equilibrium. I'll touch on some of these in a little bit greater detail as we go through the talk. But a lot of great information that I'm presenting today comes from a couple of wonderful resources. The IPEM Report 103, which is this book shown on the left-hand image here, on small field MV photon dosimetry, is an excellent resource, as is the joint publication from the IAEA and the AAPM Technical Report Series 483 on dosimetry of small fields. So, what is a small field? We have to understand what the conditions are before we can really dive into what sort of concerns we have with them. So TRS 483 defines small fields as having at least one of these conditions: either loss of lateral equilibrium on the beam axis, partial occlusion of the primary photon source by the collimating devices, or that the size of the detector is similar to or large compared to the beam dimensions. So with that in mind, let's step through some of these challenges and see what we can learn, what we can do about them, right? So first is physical size. Small fields are generally in the range of 4 to 40 millimeters, but how you define that field size does matter in terms of how you need to approach measuring these fields. So are you defining the field size by the jaw setting, or are you defining the field size, say, by the full width half max? This illustration out of a publication from Indra Das's group, and I think it's reused in some of those other books I was pointing to, illustrates that on large fields, your full width half max generally correlates with your jaw settings. But as you decrease, because of this overlap of the penumbra that's formed by those two collimating jaws, or even a cone or something like that, your full width half max starts to sink down in this curve and become wider than your jaw settings. So your actual field size may be wider, although your peak is lower. So it's something definitely to be aware of, especially as you're picking detectors for these. We notice the decreased output as this peak goes down, but then it seems obvious, but again, sometimes it's good to state the obvious. Alignment is very critical in these small fields because of their size. A very small misalignment turns into a large geometric or dosimetric miss on your measurements. Second issue is source occlusion. For those who don't know what this means, is that as your jaws come together, or your collimation system, you're actually blocking some of the primary photon source to that measurement point at the center of the field. And that can affect both the spectrum that your detector sees as well as the output, or the actual doses that are measured there. Lateral electronic equilibrium is the third issue on our list here. Generally, the equilibrium condition is when your lateral scattering distance is equal to or greater than the range of the electrons that you've set in motion within that medium. So practical translation of that is that as your energy increases, as you see on this plot, the plateau decreases. So you'll start losing that flat region in your field generally when your beam width is less than 2 times your Dmax value. So higher energies do lose that plateau sooner, which makes your detector positioning, your detector perturbations, all of these small field considerations come into play a whole lot sooner for the higher energies than they do for your lower energy beams. So what that really comes down to in terms of what you can do about it and characterizing your field is that it's important to understand and to characterize the profiles of your beam, not just the output factors, because that will help you understand better what's going on with your fields, especially in these changing energies or high energy fields. So away from the fields themselves, you have to consider the detectors, right? So the detectors impact your measurement in a multitude of ways. The first and most obvious, again, is size and shape of your detector. So you will average the signal across the region of collection of your detector. We like to talk about spot size for a detector, being that region of actual measurement for your collector wall and in this case ion chamber, the electric field that directs those ions to the central collection electrode. Your profile relative to your detector spot size is one of those conditions that determine a small field. So how big your detector is, how much you're integrating over. This image is actually from a publication from Meltzner and DeWord looking at gamma knife helmets. And while the spot size of the detector is small enough to fit within that 8mm helmet, the buildup that's required on either side does take you, in order for that charge particle equilibrium, takes you outside that plateau. So really it is your detector spot size, how well it fits within the field. But if you're putting an air cavity this size into a field, then you're affecting the field all the way out to where those charged particles are coming from, because you're perturbing your beam there. So you need to accurately determine that size of your detector so that you can step down the road to making those proper corrections. Consistent and accurate positioning of your detector is critical, so that you're positioned in those, especially on these small fields, that location that will give you the maximum signal if you're doing output factor measurements, for instance. But if you have a larger field, then that also smears out your penumbra because of the region you're integrating over. And so you may need a couple of different detectors really to fully characterize those fields. For a film, in general, film is great for those profile determinations, but as you get down to really, really small pinpoint fields, there are some issues with scatter within the scanner that may affect the resolution at which you can really determine the shape of the field. So I haven't encountered this outside of brachytherapy, but if we get down to pinhole fields that I know some people are moving into, there may be some film issues in terms of the scanner resolution. Second issue from your detector itself, I guess I mentioned in the prior screen, is perturbation of the beam. So when you change the fluence right there at the point of measurement, you alter the dose by replacing water with your detector, you change your measurement, right? So the things to consider: if you have an ion chamber, how big is that air cavity? What's that spot size? If you have a diode, what's the density of your diode? How does that affect it? Is there a built-in compensation? So compensated diodes usually have an air gap next to that higher density diode in order to try and balance out the interactions. So that can decrease your energy dependence. That's the idea of the compensation. But if you have a compensated diode, you really need to understand where the target was for that compensation, where it was designed to have good response, because they can behave worse outside that region than a non-compensated diode that's a little bit more predictable sometimes. There are often published corrections to account for this perturbation. One example is shown here from Paula Francescan, where you can see the ion chambers need a higher than 1 correction because they under-respond because of the lower density of the air cavity. Diodes need a less than unity correction because they're over-responding in those low energies. Or excuse me, the small field sizes because of the density. So if you're using published corrections, though, you do need to be aware of the all of the conditions that went into determining the published corrections so that you can match those as much as possible, obviously, while you're doing your measurements. Another example of some of the publications, again, from Paula Francescan, there's an array of diodes and our X-ray and W1 scintillator and a collection of ion chambers, as well as the microline, which is the liquid ion chamber, just to kind of illustrate some of the differences and the range of corrections that may be needed depending on your depth in this one, I think. So, third way that your detector is going to impact your measurements is the signal level. So with an ion chamber, your signal is proportional to your collecting volume. So as those volumes decrease and you get down into these very, very small microchambers, your signal goes down and your signal to noise ratio becomes more of a concern. You do need to ensure that you have an appropriately sensitive electrometer and good quality cables so that you can measure those very small signals very accurately. A diode is useful in that it has a larger signal. It generates a much larger signal than from those microionization chambers, but there are obviously trade-offs with the diode as well. You need to be aware of signal to noise ratio issues. Decrease your uncertainty by understanding if you have leakage, how much leakage you have from your electrometer, making sure your electrometer has a proper warm-up before you're making measurements with it so you're as stable as possible. You need to make sure you match your signal strength with the proper electrometer range. You'd be amazed at how many times we've seen people trying to make very, very small measurements in the high signal range on their electrometer and then complaining that things are unpredictable or unstable just because they don't have the sensitivity in that range for the detector that they're using. There also can be some effects from a triax cable, which is where I say you need some good quality cables. Old kinked bent ones are not so good for your really small signals. And there can actually be some physical stresses within that cable if it's wound up tight and then unwound right before measurement that generate some triboelectric effects, some spurious currents as that cable relaxes. And so if you have to wind up and unwind your cable, it's best to unwind it as early as you can. Let it sit for a little while to relax. If you're winding it up, don't wind it as tightly as possible, just to decrease some of those physical stresses on it. If your system won't hold at zero, that's something to look at. It could be an effect from your cable, especially if it was just unwound. There's also cable-induced signal if you're irradiating cable that can cause some issues with your measurements, although that's a little less critical with these small fields because you're less likely to have something looped in the field. Accuracy of your detector is something also to understand. Does your detector have energy dependence? For diodes, for instance, often diodes can have a low response out of field because of the lower energy of the scatter out near the edges of the field, and therefore you can potentially underestimate a very large region of low dose in your SRS patients because you haven't characterized those tails of the field. Again, be aware if you have a compensated diode that may be useful, or it may be a hindrance as you're making those measurements, depending on what the compensation was. Corrections for diodes, or if you have energy dependence, a detector with energy dependence, as you're measuring depth doses, your corrections may also be depth dependent because of the change in spectrum as the beam is attenuated. And be aware that energy dependence will also mean that any change in the scatter conditions will also affect your response because of the low energy of the scatter. If your detector has angular dependence, that can affect your accuracy as well. So the advice really is, my advice, is to use your detector in the orientation for which it was designed. That will help minimize your angular dependence. Or if you're doing something in a different orientation, investigate and be aware of the implications that might come with that change and with any angular dependence that might appear. Detectors also can have dose rate or dose per pulse dependence, especially in ion chambers in the dose per pulse region, because of just the mechanism of the ionization and collecting those. So in order to make sure you're counting that for that correctly or using the right detector for that, you do have to understand both your accelerator and your detector. When you turn up the dose rate, is your accelerator just generating additional pulses, or is it actually a higher dose per pulse, etc. I've talked about ion chambers and diodes a little bit. I have not gotten into gels or film, OSLs or TLDs. The other things that may come into play, of course, leakage, drift, repeatability, how long it takes for film to develop, what's the resolution of your detector, can it be calibrated? All of those things do come into play for a variety of scenarios. So that leaves us with this puzzle of really what should we do? There's a lot of stuff to consider when you're looking at small fields. There are a lot of potential holes to fall in. Sometimes it feels a little bit more like a ticking time bomb when you're told, we're going to start an SRS program, commission my small fields for me. There is hope. I'd like to offer three main options for megavoltage beams. One is established technology, although with known perturbation issues, and there I'm referring to the X-rayed diodes, the D1H and the D1V. There's new technology, although it's not as new now as I guess I could have said a couple of years ago, but the X-rayed W1 and W2 plastic scintillation detectors are wonderful water equivalent detectors. And then there's the old standard, finally working properly in miniature form, the X-rayed A26 microionization chamber. So each of these detectors, as any detector does, has both strengths and limitations. And really for small field dosimetry, the best solution is going to be a good combination of complementary detectors. So a little bit about our diodes. The D1V and the D1H are unshielded diodes. It's the same diode for both, just a different housing. The H for horizontal was designed for use in solid water phantoms. And then the V, the vertical version, is designed for scanning so that you're not perturbing the field with the stem of the chamber. So it would be held vertically for scanning. They both have a 1 millimeter diameter spot size, and there are some published correction factors available. There are a couple publications in 2014 that looked at both measured and calculated factors. So you can see D1V in green here, and then the W1 scintillator in the black, and the, where'd it go? This one was perpendicular to the beam, so that's why the offset there. Strengths of the diodes. are that they really are well-established technology. Diodes have been used for quite some time for scanning measurements. They have minimal volume averaging just because of the smaller spot size of 1 millimeter, and a relatively low angular dependence. Although if you're talking output factors or pure scanning, then if you're using it in the intended orientation, you don't have to worry about that. Limitations are pretty standard for diodes. They're not water equivalent. You do have to correct for the density of the diode. Here's the green line for our diode compared to some others. There is a correction. There are some publications here that talk about that, but it's a diode. It's not water equivalent. And of course, some angular dependence, as with most diodes. Second option that's new technology is the X-ray and scintillation detectors. They are an organic scintillating material, either 1 by 1 millimeter or 1 by 3, depending on which fiber you've got. They're water equivalent, which is really nice because now that perturbation of the field right there at the point of measurement is eliminated. You're actually measuring the conditions as they would be without the detector in place. They do require a correction for the Cherenkov effect, which is basically manifests as a stem effect, where Cherenkov light is generated within the optical transfer fiber next to the scintillator. And so it creates this additional signal that must be removed because it is field size dependent. It's dependent upon how much of that fiber is being irradiated. They're also not an absolute dosimeter. They do require comparison with a known or with a calibrated dosimeter, like a calibrated ion chamber. And as the material accumulates dose, it does degrade slightly. It's a plastic. Plastics tend to yellow underneath radiation. And that changes the spectrum slightly and changes the signal level that's transmitted. So it does need periodic recalibration. Both the CLR means Cherenkov light ratio and if you're using a dose calibration on it as it ages. The method that we use for correcting for Cherenkov is a 2-channel chromatic correction. So really, there's a question that popped up. Let me see. How much does it change with dose? You lose about 2% per kilogray in terms of signal degradation. For getting rid of the Cherenkov light, removing that stem effect, we use a published 2-channel correction where we split the light up into a blue region and a green region. We have you do a couple of characterization measurements, and I should have replaced this with the water scanning one, but this is the slab that's sent with the W1 scintillator, which is the original point dose measurement system. And we'd have you do a minimum fiber configuration measurement with the fiber coming straight out of the field, and then what we call a maximum fiber configuration with the fiber wrapped around within the field. And the idea here really is that you're keeping the dose to the scintillator constant and just changing the amount of optical fiber that's in the field. So only the Cherenkov contribution changes. We then calculate this Cherenkov light ratio based on the change in signal in each of the 2 channels. And with that relationship established, we can now use the signal in the green channel to remove the Cherenkov stem effect from the blue channel in order to get your actual measurement. And if you're doing a dose calibration, you would give it a known dose in a reference field size, reference depth, and then that becomes just a scaling factor that's applied to this corrected signal. There's a question, do I have a curve plotting response versus dose? I don't have one here. It does depend a little bit on the field sizes that you're delivering. If you're delivering lots of dose from larger field sizes, then your signal will decrease a little faster than it will just with small fields. And then there's a question from Philip about whether there's a difference in the CLR value that you get if you're using the bracket that we send with the W2 for use in the water tank compared with this larger field solid water. There shouldn't be much difference. especially at the beginning, but as your fiber ages, there may be a slight difference depending on how much dose is received at this front part of the fiber. The smaller field actually is probably the better representation because it uses just a bit less of the fiber for the Cherenkov characterization, since the Cherenkov spectrum may be a little bit different further down the fiber where it hasn't received as much dose as it would be right up there close to the scintillation, or the scintillator itself. Good questions, though. The W1 scintillator was the first version that we released. It was the very first commercially available scintillator. It had a 1 millimeter diameter, 3 millimeter long active scintillation region. There are a number of publications on this one because it has been on the market for a while. But the one that I'm always excited to be able to share with people is that TRS 483 publication lists the W1 KQ as unity. It's the only detector in the entire publication that shows up in these tables with no correction factors needed, really. So that's always reassuring when you're going to measure some of these small fields, that there's an additional complexity that's been removed. Strengths of the W1 is that KQ of 1, beam quality correction factor, doesn't need to be determined as your field sizes are changing and as your spectrum shifts with those small field sizes. It is water equivalent for megavoltage photons and electrons. We have not seen dose rate or energy dependence with it, and it does have it has negligible temperature dependence. If you were to try and measure someday, if we're FDA cleared for on-patient measurements, then you may need to do a correction between the room temperature calibration and a patient skin temperature sort of measurement. It has about 0.1% per degree temperature dependence. But if all of your measurements are at room temperature, like these QA measurements are, then that's not something that you need to consider or worry about. Limitations of the W1 is that it was designed as a single point measurement system. It was not designed for scanning or for, it's a small field detector. It's not designed for large fields. It does have a fairly low signal to noise ratio, so there is a higher uncertainty out of field with those measurements. I didn't mention it does need to be used with the 2-channel electrometer like our Supermax in order to do that Cherenkov correction. Excuse me. As I mentioned, it does require a reference dose. It requires occasional recalibration just because of dose damage to the fiber. And one that I mention here is that there is a little bit of a learning curve, only because we're used to ion chambers, we're used to diodes, and we're pretty sure we understand what's wrong when things don't look quite like we expect them to. Optical signal measurements are a little bit more non-intuitive to many users. So getting some experience with it, doing some measurements with it so that you become accustomed to the behavior of the scintillator really does help you as you go into further measurements. With the W2, we integrated the optics collection as well as the electronic signal processing for that Cherenkov removal into one single electrometer here with a removable optical fiber. So now we can provide both a 1x3 that matches the W1 fiber and a 1x1 millimeter fiber. And the reason we were able to go down to 1x1 is actually because with this integration, we were able to both increase our optical sensitivity and decrease the electronic noise within the system, because now we've eliminated some of the longer connection fibers and the additional electrometer, so that we could get good quality measurements with a reasonable SNR, even with that smaller detector. So this dedicated system, the MaxSD, I guess I mentioned, I should look at my bullet points, does combine the optics and the signal processing electronics. You can do your characterization measurements with this device, and it will store them and be able to apply them to subsequent measurements. You can also perform point dose measurements directly with this device, no additional electrometer required. The MaxSD will also perform a fast correction, Cherenkov correction, so it takes that input signal, processes it, and then outputs every 10 milliseconds through a triax cable, an analog output, just a current signal, that can be read by your water tank scanner, or a scanning electrometer. And so that way you can scan your small fields with this detector using the software for your water tank. You do have to scan slowly because it's a low signal device, but you can get some very excellent results that way. From the perspective of the water tank, it really looks like scanning with a diode, where you're not applying bias to the detector, but the water tank electrometer receives a current when the beam is on. So we were able really to keep the strengths of the W1, it's the same scintillator at the end of that fiber, it's the same fiber, it's the same construction method, and we were able to eliminate a couple of the limitations of the W1. The microionization chamber option, the A26, was designed actually as a result of Jessica Miller's Ph.D. thesis investigation, where she looked at the strange behavior of all of the microchambers that were on the market at the time. And most of this oddity was manifested in the polarity response of the chamber. There were some nonsensical sort of polarity behaviors with microchambers. And it was not model specific. It would change between detectors of the same model, nor was it vendor specific. It's not like one vendor had this issue and others did not. Every single microchamber on the market had issues. And so as the result of her work, we were able to design the A26 to overcome those limitations and to really be designed as a reference class chamber for small field measurements. So some of the things we asked ourselves as we were designing this, beyond, of course, the requirements imposed by what Jessica found, I should say Dr. Miller, what Dr. Miller found, we were trying to construct it with a spherical spot size or circular spot size, so that it didn't matter if you were what the orientation was of your chamber with your for scanning. Your volume averaging would be the same. We modeled the electronic fields so that we could verify that shape and ensure that we knew the volume well. Chamber volume, of course, is as small as we can make it for this one. I don't think you'll find a well-behaved chamber, especially in terms of the polarity effect, any smaller than this, just because it's as small as you can machine this sort of conducting plastic. So a lot of people compare with our smallest chambers, the A16. It does have a wire electrode rather than that conducting plastic, and it's a 0.007 cubic centimeter volume. The A26 doubles that, it's 0.015, but the spot size has increased by only 0.8 millimeters. So we didn't stretch it out very much, but you've doubled your signal level from that, as well as getting a chamber that behaves much more properly, I guess. And the other thing we considered, of course, is, as I mentioned, doubling the signal. Will the SNR be sufficient for the intended use? Can we make sure that users have good signal level from this chamber? So strengths of the A26, it is that reference class ion chamber. It does have that spherical spot size, so it's independent of orientation. And the ion chambers are familiar technology for most physicists. We understand if they're what their dependencies are and what we need to look at if things look odd. Limitations of the A26 is a limitation of any ionization chamber. You do have to correct for the air volume because that changes that fluence beam interaction right there at the point of measurement with the decreased density. So mostly I've been talking about small MV fields. I want to just briefly throw in the A20. This is designed for small kilovoltage X-ray fields. It's a very small parallel plate chamber in the tip of this detector. So it's meant for beams coming at it from the front face. So a low energy X-ray chamber for small radiation fields. It could be used for X-rays for, whoa. I don't know what I meant by that, but stereotactic and TG61 compliant. Oh yes, for superficial skin therapy. it has a just less than 2 millimeter collector diameter, and it has very excellent energy response, all from low kilovoltage energies all the way up to cobalt 60. So electronic brachytherapy as well as small X-ray fields. When you're doing these small measurements, it would be negligent of me not to mention the need for a very high quality electrometer. So these are our two primary electrometers. The Max 4000 Plus is the workhorse. It's a very robust single channel reference class electrometer. This is your do the job every day sort of electrometer. It's a wonderful, wonderful electrometer. The high-end electrometer is the Supermax, which is our 2-channel electrometer, has a little bit higher resolution for some of the low-range measurements, and it has a shorter warm-up time. The important thing on both of these, besides the fact that, or I guess that illustrates the fact that we really stand behind our products, is that both of these have an industry-leading 5-year warranty. We have a lot of experience making electrometers, and we are proud to say we make very good and solid and stable electrometers. So with all of that, I know that's a lot to absorb, but together we'll get through this. We're happy to help you with your small field measurements. Let me know if you have questions right now. Please feel free to enter them in the question dialog box. Otherwise, feel free to visit our website for more information, or contact your sales representative, sales@standardimaging.com. We're happy to talk to you more about any of these detectors or any questions you might have about small field measurements. Otherwise, thank you all very much for your time today. It's lovely to have you here on a cold February morning in Wisconsin. Hope you're doing well wherever you are. Oh, there's a question. Norman asks if the fiber for the W1 or W2 is replaceable. The W1 is actually connected or potted directly to the optics, and so in order to replace the W1 fiber, it needs to come into standard imaging. A W2 fiber is user replaceable. You just get a new one from us, buy a new one and plug it in. So you can have multiple W2 fibers to be used with your Max SD electrometer. Russell asks if the W2 can be used with a beam scanning system. Yes, absolutely. Really, it doesn't matter which scanning system you're using, because the Cherenkov correction and signal transfer from the optical signal into an electronic signal is handled by the Max SD as just a pass-through. And therefore, if you're scanning with it, your water tank really just thinks it's a diode. It doesn't need to apply bias, but it gets signal when the beam is on. Up to which field size would you suggest to use a W2? I wouldn't go above 10 by 10, really. There are a lot better detectors for that. The other issue, I guess, is that if you're scanning with it, you have to scan slowly, just because of the signal levels that you're getting from the detector. So we recommend about a 1-second dwell per measurement point when you're making your scans. And that's quite reasonable when you're doing very small fields, because it's critical to get that good quality measurement for those very small fields. It's a little bit time prohibitive once you get up to large fields, especially when there are good detectors that do that very well. And I guess that's another area where I say a good balance of detectors is really needed for these small fields. Norman asks, what's the smallest square or cone size that can be measured with the W1 or W2? Really, that depends on your fields. I have seen, you know what, I didn't have that in this talk. I have seen very small targets measured, a few millimeter targets measured with the W2, but the limitation really is how much correction are you willing to make. So if the 1 millimeter diameter detector is going to have significant volume averaging because you're measuring a 1 millimeter size field, then no, that's not appropriate. But if you, I guess, have characterized your penumbra better, well with film, say, and you can account for the volume averaging, then it's up to you to determine on the energy of your beam what your volume averaging is, so that you know the limitations at which point you need to stop using those detectors. When would you use a 1x3 scintillator and when a 1x1? So the 1x3 is extremely useful for scanning the slightly larger small fields, I guess, say above a centimeter, 1 centimeter or above, because you get 3 times the signal from it. And so your noise decreases, or your signal to noise is higher. And you could potentially scan just a little bit faster, or at least get smoother scans with the 1x3. The 1x1 is highly critical when you get down to those very small fields, say below a centimeter, when the 3 millimeter integration along the length of the scintillator for the 1x3 starts to become a hindrance, and starts to become to impact the output measurements just by virtue of the volume averaging along that 3 millimeter length of the fiber. So hopefully that makes sense. Hopefully that answers your question. These are great questions. Anybody else? Well, I can hang out for just a little bit longer if anyone does think of a question. Otherwise, thank you all so much for your attention. Watch your email either later today or tomorrow for a link to the recording. Feel free to share with colleagues or go back and look. And if you have additional questions, don't hesitate to reach out. I'm always happy to talk with people about these detectors.